All right, so chapter 2 is all about kinematics. Basically one-dimensional and eventually two-dimensional motion, otherwise known as kinematics. We talk about gravity, and it's the picture of cheese falling because of gravity, and because it looks really good. And I like cheese and pizza-like things. Everybody does. Enjoy. All right. Excuse me. Displacement: a vector that points from an initial position to a final position and has a magnitude equal to the shortest distance between 2 points. That is displacement. The distance itself is different in displacement. Distance is a scalar, displacement is a vector, so it has to be either negative or positive to indicate that it's a displacement. Well, what does the difference look like? Well, let's show you. Let's say we start here from point A, and we go do. Oh, right, I'm at point B, and then we go do. Okay, I'm at point C. And let's call this 1 kilometer and 1 kilometer. So, and let's say there is a troll in the way, and it has 4 arms, okay, and it's angry. So you want to go this way, but you can't because there is a hairy troll in the way and you can't get to C. So you have to go to B, and then you have to go down to C. So your total distance that you traveled is going to be 2 kilometers. It's just 2 kilometers. It's a scalar value. Your displacement, on the other hand, give a little picture here, would be as the crow flies. I think it's the term a lot of people use. And so your displacement is not going to be 2 kilometers. It's actually going to be the square root of 2 kilometers. Where did you get square root of 2 kilometers from? Well, remember, this is a 1, square root of 2. It's a 45, 45, 90 triangle. 45, 45, 90. And so your displacement and distance are 2 different things. Additionally, as I have it now, it's just a scalar. It would actually be square root of 2 kilometers, let's say at 45 degrees south of east. So that way I gave it a direction, and that's what makes it an actual vector. So that's kind of a simpler description of the difference between displacement and distance. Another thing to note is, and I probably will talk about this later, but just in case I don't, speed is generally going to be your distance over time, whereas your velocity, which is what we really deal with here, is your displacement over time. So don't get those two confused. Speed is always a positive quantity. It's like that super positive person that annoys you all the time. Well, their speed, which kind of means something else now that I think about it. But you get what I'm saying is speed is always going to be a positive quantity. An example of that is, if I decide to drive through Eastboro backwards at 30 miles an hour, my velocity is going to be negative 30 miles an hour, but they're still going to say my speed is over 20, and they're going to give me a ticket and probably something else for reckless driving, in hindsight. But I've never done that, so I don't really know. But in theory, that's what they're going to do because they don't really care about your velocity. They care about your speed, your absolute value. So that's kind of something to note on that. Okay, and I did talk about that. Here's kind of written it out a little bit better. Average speed is distance covered by time, and velocity is speed with direction. So that's really the difference. The speed has a direction, and that will give you velocity. And these are 2 basic equations, and you probably remember these. They're nothing special. Well, why aren't they anything special? Well, because in algebra, things haven't changed. So far they haven't. RT is equal to D. Your rate times your time is equal to your distance. That's the same thing as this. It's saying speed times time equals distance. Velocity times time is equal to x, or displacement. And so the dirt equation, so to speak, is what some students strangely call it, is essentially what we're using here. So, all right, let's do an example problem dealing with speed, velocity, etc. The bike below, which I'll show you a picture here in a second, can cover 398 meters in 10 seconds. It's a lot. What is the average speed of the bike at full power? So this bike below is this guy right here. It is an actual recumbent bike. Very aerodynamically designed, and it was designed by this team right here. I believe it's a Dutch team. And I believe this is in the Nevada desert because, you know, when we're going to test stuff, we need to go out to the desert, Utah, Nevada, whatnot. So they took this bike and they could cover 398 meters in 10 seconds. So we're going to figure out what that speed is. Okay? Speed is distance over time. And so I take, okay, that's 398 meters divided by 10 seconds. And that's going to give me 39.8 meters a second. Pretty simple problem. 39.8 meters a second doesn't make a lot of sense to you because, you know, if I'm driving down Woodlawn, it doesn't tell me that the speed limit is like 24 meters no, that wouldn't even be 24. Like 18 meters a second. No, it says it in miles an hour. So what is that in miles an hour? Well, it is 89 miles an hour. A pedaled bike went 89. This problem is about a year or two old, so they may have broken the record since then, but that's pretty insane. That's one of the reasons I do this problem. The other reason is the second part. This will kind of prepare you for a more tougher homework problem. So we have that bike, and it then slows down to a constant 20 meters a second for an unspecified amount of time. And let's say we have the overall average velocity in this case. We're assuming it's in the same direction. The bike is 25 meters a second. How long did it travel at 20 meters a second? So scrolling down here, we know in this case it says velocity, but it could mean either one since we're going in the same direction. And so we're going to say, all right, well, I know that my average speed is going to be my total distance traveled over my total time traveled. Okay, well, that makes sense. If I cover, I don't know, 400 miles in an airplane at 1 hour, then, you know, that's my velocity, 400 miles an hour, which is for smaller airplanes, I think. Smaller jets, rather. Okay, so, well, let's figure out what that is. Distance total. Okay, well, I know in the first leg I went 398 meters. What I didn't know was how far I went in the second leg, I'm going to call D. I know it took me a amount of time of 10 seconds to do the first leg. The second leg, man, I don't know. Let's call it T. But I do know that my overall average speed is 25 meters a second. Alright, so this is where you get stuck. You're like, oh, what the crap? I've got a D and a T. I got two unknown variables. I can't solve it. It's insolvable. Well, yeah, it actually is insolvable if I can't find something else to do with it. But I do know one thing. What do I know? I know that the second velocity was 20 meters a second. And I know if I take that velocity times that by time, I will get a distance. Now, we're trying to solve for time. So I could take this right here, which is true. We just don't know time and distance. And then I can go, all right, let's do something with you. And I'm going to substitute you in right here. So then rewriting this, and I'm going to move the 25 to the other side for simplicity, is going to give me 398 meters plus 20 meters a second times t over 10 seconds plus t. Alright, so now I got to get the t out of the denominator, so I multiply that side by that, and then I get 250. Notice that the meters over a second times a second is just going to give me a unit of meters, so it's always good to carry your units. I know it's really annoying, but it is really useful. It can get you out of a lot of pinches sometimes. If you don't get the right units, then you may have known you did something wrong. So, then plus 25 meters a second times t equals 398 meters plus 20 meters a second times t. All right, so I need to get all my variables to one side. So 25 minus 20 is going to give me 5 meters a second, t. And then I take 398, subtract 400, and that's going to give me 150 minus 2 is, what, 148 about said? Meters. Notice that meters now cancels out, and that your only unit left is seconds. And so you divide both sides by 5. And so when I take 148, divide that by 5, it gives me 29.6 seconds. I'm going to write that over here because I didn't write that over here. All right, so 29.6 seconds. This is similar to one of your homework problems you're going to have. It's a little bit more difficult, obviously, than the first one, but it's a very similar setup that you're going to have to do. One other thing you might want to remember, and I can't recall if it comes up in the problem or not, is that an average speed, let's say AVG, is nothing more than one speed over one speed plus the second speed all over 2. Because it's like, okay, well, if I get 100 on my first test and I get a 50 on my next test, my average test score is a 75. So keep that in mind. So. All right, so instantaneous velocity. We're not always going to be dealing with average velocity. A lot of times we're going to be dealing with instantaneous velocity, which is the velocity at a certain instant. Essentially put, I can maybe draw a picture of this a little bit better. If you haven't had calculus, this won't make a lot of sense. If you have, you're basically taking the limit as your time approaches 0. Calculus isn't required for this class, but I'm just showing you that if you happen to have it, that might make some sense. A more graphical way that I'm going to show you to understand it is, let's say I've got, I don't know, let's make a little XY distance versus time axis. And let's say I'm doing this. Woo! So basically put what the limit really means, or what an instantaneous velocity is. Let's say this is 0.1, and let's say this is going to be 0.4, and then let's call this 0.2, and then let's call this 0.3. I could figure out the overall average velocity by taking my total distance divided by total time, and it would give me this slope right here. That would be the average velocity for the whole motion. But would that be that accurate? Not necessarily, because, I mean, you start off a lot slower to it, and you finish off at that velocity. But it's not going to do a good job of characterizing your velocity the whole time. You know, if you take a trip, you're going to have to slow down sometimes. You know, someone in front of you is on cruise control and is taking 8 miles to pass the guy. And then when you finally do, you're really pissed off, so you fly by them. Yeah, your velocity is not going to be constant. So what you could do is you can break it up into different chunks. I could break it up into the 1-2 chunk and the 2-3 chunk, and then we can even do a 3-4 chunk. And basically, you just do smaller and smaller and smaller chunks until at some point you're going to create a line that's going to be tangent to the curve. Tangent. The actual definition of tangent from your geometry class. And at that point, you have what's called the instantaneous velocity. So basically what instantaneous velocity really is, you're just finding a smaller and smaller average, so that average is at an exact point in time so that you know the velocity. So probably more than you need to know, but that's what it is. And in practice, instantaneous velocity is generally measured by speed traps, radar. This is a speed trap. It is in Victoria, Australia. I went there 2 summers ago, and they're notoriously bad at giving you tickets. It is not uncommon for a person to go there and come back with thousands of dollars of tickets because they didn't even realize it. They put these all over the place, they hide them, and then they just take your ticket and they mail it to you. And they have an extremely low tolerance in Victoria. In fact, 1 to 2 kilometers an hour over the speed limit, and they'll give you a ticket, which is like a mile an hour, which is insane to us Americans. But yeah, that's other country for you. But speed traps, so that's what really exists. It takes your instantaneous velocity. It doesn't care that I may have been going, 100 kilometers an hour for a whole hour on average. It just cares about that one instant in time that I happen to go 102 kilometers an hour. So, sorry, that wasn't Victoria. That was Queensland. I lied to you. I was in Victoria, but that's where I got the picture from. Queensland's not as bad. It's more the state of Victoria. So, acceleration. Acceleration is the change in velocity, either positive or negative, divided by the change in time. We call it delta v over delta t. And like the average, there's also an instantaneous acceleration. It would be the same setup, except instead I'd have velocity versus time, and you'd have a changing velocity, and you'd have to, kind of find smaller and smaller and smaller chunks of velocity until you have that instantaneous acceleration. So, we're only going to be dealing with a constant acceleration. There is an acceleration that changes over time. It's called jerk. But we're not going to get that far in this class. It's more something you wouldn't even get into until you took like mechanics, which is a upper division physics course. So, but yeah, that's your definition of acceleration. All right. So, let's do an example problem, another one. This one involves emus. They're a really fun little thing, little bird, and they run around. There's one here, and then there's one here, and they don't shut up all night long. They pretty much make noises all night long. I learned that when I was in Australia. Anyways, let's assume they can reach speeds up to 48 kilometers an hour, around 30 miles an hour, just to kind of give you an idea. We assume that an emu starts from rest and reaches this speed in 5 seconds. Was his acceleration? So a big part of this is just kind of showing you the equation that I normally use. We know that, try to find my cursor here, we know that acceleration is equal to the change in velocity over the change in time. And what is change in velocity? Nothing other than v minus v I. It's usually v naught, but I've been doing i's lately, so let me be consistent with the book. Let's go v naught, sorry. V naught means velocity at time 0, so I just simply call it v naught. And then delta t is actually t minus t naught, but we usually start off at time 0, so 0 times, so it's t minus 0 is t. And so if I multiply both sides by t, I get at is equal to v minus v naught, or I can say v naught plus at is equal to v. This is usually the equation I use. You can use the top one. It's the same thing. It's just expressed differently. It's like changing an outfit. You're the same person, but you're wearing a different outfit. This is the different outfit. This is having platform shoes. I'm not even sure what those are. And this is having tennis shoes. Okay, I know what those are. But this one, I like it because it says, okay, this is your initial velocity. And then whatever acceleration you have, and in the time that you have your acceleration, will give you your instantaneous velocity. And so that's what I'm going to use to calculate the acceleration. I don't have to do that. I could do other things. But I will choose to do it that way. There is more than one way to skin a cat. So says the little thing, but, whatever. All right. So we're trying to... My mouse stopped scrolling, sorry. We know that the time is 5 seconds, and we know that the top speed is 48 kilometers an hour. What's acceleration? So we know it starts from rest, so that my initial speed is going to be 0, and the time is going to be 5 seconds. My final speed was 48 kilometers per every hour. Now, I need to actually convert that Because sometimes the book will give you things in kilometers an hour, since that's the world standard, more or less. And well, we can't really math with that. So, all right, well, I need meters a second. So for every 1 hour, I know that there are 60 seconds in a minute, 60 minutes in an hour. 6 times 6 is 36. 2 zeros left over gives me 3,600 seconds. And so hours cancels. This would give me kilometers a second. Not quite what I wanted. Wanted meters a second, right? So, okay, for every 1 kilometer, there are 1,000 meters that occur. 1,000 meters. Then I get Mr. Calculator here and plug that in. And I get 13.3 meters a second. Okay, so now I use this equation up here. I say, okay, well, 13.3 meters a second equals 0. Don't have to put it in there, but for good measure, I did. A times 5 seconds. So I divide both sides by 5, and that gives me an acceleration of 2.67 meters per second. Then divided by seconds, so it's meters per second, or it could be meters per second squared. Lot of you side note. So I'm going to get this at least once. Side note. Bam. So when you have a meter per second, and then when you divide it by a second, that's going to give you meters per second squared. I say this because a lot of people, let me try to scroll where I get some room to write here. A lot of people will think, okay, well, that's just going to cancel out. Well, it doesn't, because you'd have to have meters per second per 1 per second, so that the seconds would flip all the way up to the top to give you a meter second per second, and then you get meters. This is not right. This meters per second squared, that's right here, is correct. So it's either meters per second squared or meters a second. Or meters per second. I'm generally going to say meters per second squared, mainly because it's easier to write. Sometimes when I type it out, I may put meters per second, because then you have to, find your superscripts and stuff, and that's not a lot of fun. But I guess to each his own. So, anywho, there's the emu problem. So that's an acceleration problem. I had left myself room there, and I didn't even realize it. Oh well. I mentioned earlier that we will be dealing with constant acceleration, and there are plenty of constant acceleration equations out there. There are special equations derived to deal with situations like gravity, where it's always going to be a constant acceleration. Gravity is roughly 9.8 meters per second squared. If you had calculus in high school or college, they deal with 32 feet per second squared, but this is a physics class, so we deal with metric units, so 9.8 meters per second squared. The gravitational pull of the Earth is different depending on where you're at. The higher you get in latitude, i.e. the closer you get to the poles, it can get as high as 9.82 meters per second squared, and it can get as low as, I believe, 9.78 near the equator. And that's because the Earth is not a perfect sphere, and I'll talk more about that in Chapter 4. But 9.8 is roughly what it is, at least in Wichita. So I have a little proof that I'm going to do. So let's do that. So I gave you one equation. That's the V equation. Well, let's do a couple things. I know that the average velocity is equal to my initial velocity, V, plus my second velocity, V naught, plus my second velocity, V, divided by 2. And I kind of talked about that already. That's an average velocity. Okay. And then I also know that V is equal to V naught plus AT, and that's from earlier. And then I also know that X is equal to velocity times time. Specifically, earlier it was delta X, but I'm leaving off the deltas for the time being. This velocity right here is a constant velocity, so it's actually an average. And so what I can do is take a substitution and say, okay, well, this will be V naught plus V over 2. Really bad writing there. I know what you're thinking. That's some terrible writing. You got S's in second grade. I would have given you O's. Yeah, we had O's. I don't even understand what that is. I guess it's an F. I'm surprised I didn't get them. Alright, this is better. Okay, so now this equation would work if you know the initial and final velocity and also the time to get your displacement. That's good and dandy, but what if you just have the acceleration value? Well, this v is also equal to v naught plus at, so I'm going to make a super duper substitution. V naught plus at. I'm going to put it in parentheses and say, hey, I made you a substitution over v naught over 2, and that is all times t. And so, okay, then I will do another step, losing my cursor here, going back up. That's going to give me 2 v naught t plus at squared all over 2. Rewriting this gives me x is equal to v naught t plus 1/2 at squared. This is your main equation that you'll be using. In fact, these are the 2 main equations I ever use for pretty much everything except for one instance. I like this one the best because let's say you have no acceleration. Let's say you're at a constant speed. Well, if you're at a constant speed, then this equation, this whole side right here, would drop off because you'd have 0 for acceleration. And that leaves you with initial velocity, which is your average velocity. And so you would have rate times time is equal to distance. So when you do have acceleration, it gives you that extra displacement. So I kind of like the way it's written out to kind of physically address what's going on. So that's one of the main equations. There's one more that I never really proved because I don't know if it's beyond the scope of the class, but it's a long, messy proof. And that's a time-independent equation. But I'll kind of show you how I can, well, let's just give it to you. That's a little bit too long here. And that's v squared is equal to v naught squared plus 2a. And I usually write delta x. These are all actually deltas, by the way, but I kind of run out of room, and I don't always use the deltas in this class just because it's just implied. But I always write a delta for this one because for some reason my 2ax just looks really messy sometimes, and this makes it kind of help you know that this is actually a displacement here. So this one works when you don't have time and you have 2 velocities, acceleration and or a displacement. And from all these equations, I'll call this one a main one because I do use it sometimes. This can help you solve every single problem that you're going to get thrown at you. Well, how do we do those problems? Well, let me try to get to that here. Okay. I really wish my mouse would work, but it stopped working because it hates me. Okay, acceleration. Electron accelerates from around 2e5. What is that? Getting there in a second, to 3e5 meters a second in 5 seconds. That is calculator language. Well, it's not a real language, but I call it calculator language just to kind of give you a heads up that 2e5 is what you would type in your calculator, and that means 2 times 10 to the 5th. The e means times 10 to the. I will write it that way just because when I write scientific notation, it gets really, really annoying. And as you can see, looking right here, my scientific notation tends to get sloppy, but this is sizably more legible than my scientific notation. So because of that, I tend to write this way. Plus, this is how you type it into your calculator. So, anyways, that's what it means. So that means 2 times 10 to the 5th meters a second, 3 times 10 to the 5th meters a second. So that means V naught is equal to 2e5, 2 times 10 to the 5th meters a second. And your final velocity V is going to be 3e5, 3 times 10 to the 5th meters a second. And we know my time is going to be 5 seconds. We want to know how far the electron's going to travel. Also, what we don't know is acceleration. So we have a few different options that we can do, and there's multiple different ways that I can do this problem. I'm going to do a slightly harder way, just to kind of show you more examples. But I'm going to first find my acceleration, because my general go-to, since I've been a little kid, is use x equals v naught t plus 1/2 at squared. Okay, not that little, but that's the first equation I learned when I took high school physics in 98, I think it was. 99. That was the year Gonzaga got good. So yeah, that was 99. Gonzaga, sorry. Anyways, so the problem is here, I do know my time, and I know my initial velocity, but I don't know acceleration. I don't know x. So I have two unknown equations, or two unknown variables. So I'm going to use my v is equal to v naught plus at to solve for acceleration. So okay, I can do that. 3e5 meters a second equals 2e5 meters a second. I know that really sucked looking, but that's what it was. A and then 5 seconds. Running out of room. All right, so I got to plug that into my calculator, even though I think I could do that in my head. Let's just not, just in case I make a mistake, and then I have to redo the whole problem. So that's going to give me 20,000 meters a second per squared. Meters per second, or meters per second squared. That is an extremely high acceleration, you're thinking. Yes, it is. But electrons are accelerated ridiculously, especially in particle accelerators. And they can't hold this acceleration forever, but that's a topic for physics too. All right, so I have my acceleration, and I want to get distance. So I say, okay, now x is equal to my initial velocity of 2e5 times my time of 5 seconds plus 1/2 of 20,000. I'm going to write that as 2e4 because I'm running out of room. And then 5 seconds squared. I'm going to do this in steps to... Dang it, can't get to there. Where'd my mouse go? Oh, there you are. To kind of show you little bits and pieces about this. So let's do that. All right, so 2e5 times 5 is going to be, looks like 100,000. Or sorry, 1 million. That's why I do it in the calculator, just in case I make a mistake here. And so that's going to be 1e6. Notice that your seconds cancels out and it gives you a unit of meters. And then plus 1/2 of 2e4 is going to give me, that's 20,000. So 1/2 of 20,000 is going to give me 10,000. So I'm going to write it as, I'll go ahead and write it as 10,000. It's easy for you guys to see. I only did that because I was running out of room. And then that's meters per second. And if you missed that I put a squared, good for you, because I did forget the squared there. And then 5 seconds squared is going to give me 25 seconds squared. That when you square the last little value there, you're only squaring your time, nothing else. You square your time. You don't square your acceleration or the half, you just square your time. And so when I square that, I get seconds squared. That's important because on the bottom here, I have seconds squared. That leaves me a unit with meters. And then I have meters over here. That is the appropriate unit that I'm going to need to solve this problem. And so rounding out my problem, looks like I'm going to get 1, 2, 3. Looks like 1.25 million. So I'm just going to say 1.25 E6 meters, or I'll write it in scientific notation for you, 1.25 times 10 to the 6th meters. Generally large numbers. You generally will have to use this type of scientific notation in Wiley, by the way, or at least it accepts it, so keep that in mind. That's another kind of reason I'm doing this, to get you prepared. All right, so was that the easiest way to do the problem, you're asking me? Well, maybe you're not, but in my head you are. No, it wasn't. I showed you this equation earlier. You could have just used x is equal to v plus v naught over 2 times t. That would have been appropriate. But I kind of wanted to do an extra step because I don't know, I thought it might be useful. So yeah. Anywho, all right. Let's see if I can get another one in before I have to quit and do something else. Oh, I give myself room. Here I go again. Give myself room and then nothing happens. All right. Okay. Let's do another problem. Let's say a car is traveling down the road at 102 kilometers an hour until a turkey runs out in front of the car 10 meters away and freezes. The car decelerates at 4 meters per second, 4 meters per second squared, for 2 seconds. How far does the car travel? Does the turkey get hit? Okay, so a couple things. We know that our initial velocity, in this case, is going to be 102 kilometers for every hour. So I'm going to go ahead and convert that because I know I need that in meters. So I take my 1,000 meter, 1,000 meters per kilometer. Bam, that gives you meters an hour. Not really a fan of meters an hour. No one really is. 1 hour, 3,600 seconds. So, all right. What does that mean? 102 times 1,000, and then divide that by 3,600. It's going to give me 28.3 meters a second. Meters. 28.3 meters a second. It comes to a stop. Or at least we're assuming that the car is going to completely stop. Otherwise, that doesn't make any sense. So the final speed is going to be 0. We don't know the acceleration, but we do know it took 2 seconds for the deceleration to occur. And so you want to know how far does the car travel. So we know that v naught t plus 1/2 of at squared is equal to delta x. X in this case is the distance we want to get. The problem is we know our initial velocity, but we don't know our acceleration. So we have two unknown variables. So I'll treat it like I did last one by using v is equal to v naught plus at to go ahead and get my acceleration. And so that means 0 is equal to a 28.3 meters a second plus my acceleration times my time of 2 seconds. And then scrolling down a bit. Yes, I fixed my mouse so I can scroll down so it's not annoying anymore. May not have been annoying you, but at least it was annoying me. So there we go. Alright, 28.3 divided by 2. It'll be a negative 28.3 when you put it the other side. And you should get negative, we'll just round and say negative 14.2. So my acceleration is equal to negative 14.2 meters a second squared. Oh, why is it negative? Well, you're slowing down, right? If you're slowing down, the common English term is deceleration, although it's really supposed to be negative acceleration, but whatever. That's not really important. What's important is if you're slowing down, your speed is decreasing with time, so your acceleration vector should be negative. So there you go, negative 14.2. That doesn't get us the answer, you say. Well, you're absolutely right. Now I have to use the x equation. So I say, okay, well, x is equal to 28.3 meters a second times 2 seconds. Not too shabby there. 1/2 of a negative 14.2 meters a second squared, 2 seconds squared. Okay, so plugging this all in. Let's see here. Gives me, looks like 28.2 meters. Alright, so the car, to answer kind of the second question, I said it was 10 meters away, and it's going to take 28.2 meters to stop, so yeah, turkey gets hit. Yes. Turkey for dinner. We'll go with that. Yeah. I'm from West Virginia. I don't know what you guys do here in Kansas, but we're allowed to eat what we hit. So I had a friend who he hit a turkey with his windshield. I think part of it went to the windshield. It's pretty messed up, but yeah, that's West Virginia for you. Anywho, so yeah, the turkey's gonna get hit. So yeah. All right. Next up, I left myself space, but I guess I didn't need it. Okay, Epic Center. Um, Epic Center is the tallest building in Kansas. So it's pseudo iconic downtown. I believe it was created in 1989. The rumor is they were going to create two towers, roughly like, kind of mirroring each other, but funding kind of ran out, and that's just what it looks like now. But anywho, so if you're on top of the Epic Center, and I needed something to drop, so I went with a deep dish pizza because you can't go wrong with pizza. And while that sounds like a tragedy to drop a deep dish pizza off the top, something to do. How long would it take for it to hit the ground? And if we neglect air resistance, what would be the speed? So, okay, starting off over here. So these are kind of a special class of problems, and I'm going to draw me a building, and I'm fully aware that's not what the building looks like, but whatever. And so basically, we're just going to drop an item off of it. First off is, I gave it to you in feet, because if you look it up, it's going to be in feet. I think it's like 320, 325, depending on where you get your data. I went with the lower value because, I don't know what I did, I guess. And so I'm going to convert that into meters, and it's going to be 97.6 meters. So, and I kind of skipped a step there, but there are 3.28 feet in 1 meter. So, okay. A couple other things. If we drop something, then the initial velocity is going to be 0. We're not throwing it down. I mean, it would be bad enough to drop a deep dish pizza from that height, but it would be terrible if you threw it down. Such a waste of a wonderful food. Such a waste. So we know the initial velocity is 0. We also know the acceleration. We have not, I kind of talked about this earlier, but it's going to be a negative 9.8 meters a second squared. This is the acceleration, so ACC, for all falling bodies. Specifically, the negative 9.8 is the acceleration for all falling bodies that are falling towards the center of the Earth. So that's why it's, it's kind of relative that it's negative, because negative 9.8 in the United States and negative 9.8 in the clear opposite side, which is I think somewhere in the Pacific Ocean out near Australia, would be also negative 9.8, which is kind of weird because they're pointing in opposite directions. No, because it points towards the center of the Earth where we assume all the mass is concentrated. So, and it's negative. Why is it negative? Because it points towards the center of the Earth. So we know that. And then we know our x. Now this is a little bit misleading because we know y is vertical and x is horizontal. That will come next chapter, but for now, just kind of go with this. Your displacement is going to be a negative 97.6 meters because you're going to be displaced downward. And so what I want to know is how long it takes to hit the ground. Well, okay, there's a couple different equations, but I'm just going to start off with what I used last time, x equals v naught t plus 1 half at squared. We know our initial velocity, that's 0, so this whole thing goes away. We know the acceleration. We're looking for the time, but we do know the displacement, so we can use this equation. Okay. So negative 97.6 meters is equal to 1/2 of negative 9.8 meters a second squared t squared. Yay! All right. 97.6 divided by 0.5. I'm going to do this in steps here for a second. Divide that by 9.8. Okay, so notice your negatives are going to cancel, and then this is going to give me, let me show you this graphically. Meters cancels, so you're left with a unit of seconds squared. You should get on this side 19.9. Seconds flips over to the top. Seconds squared is equal to t squared. For a few of you, it may have been a while, but to solve this, you got to square root the crap out of both sides. And when you square root it, you get 4 point, we'll round it up. How about that? 4.5 seconds. And for a heavy object, this is more or less close. I would say within a couple of a tenth of a second. So any object that's heavy dropped off of Epic Center is going to take somewhere between 4.5 and 5 seconds to hit the ground. More so for lighter materials, like you drop a piece of paper. I mean that's just ridiculous. It's going to take forever. But yeah, for a deep dish pizza, I chose deep dish specifically because it's very dense. It should take around 4.5 seconds to hit the ground. So, anywho, next up is I want to know the final speed. Well, v is equal to v naught plus at. We're looking for v. We know v naught is 0, and this will be a negative 9.8 meters a second squared, and then take my 4.5 seconds. So I take 9.8, or negative 9.8 to be more exact, times 4.5, and then I get a final speed of a negative 44.1 meters a second. That is my velocity. It specifically asks for velocity. If it asks for speed, I would just say 44.1. So, close to around 100 miles an hour. It'll be a little bit less than that because of air resistance, but like I said, for heavier objects, you're not going to get affected too much. And you're not going to have too much of a difference from that height. It's not that high. It's tall, but not that tall. So, in fact, as you'll see later, I think the tallest tree in North America is around that height. So it kind of gives you a scale factor, which is kind of amazing. So. All right, so let's kind of change pace a bit. Meaning, okay, well, last problem, the object was dropped. Well, what if you indeed do throw something down? So that's where this problem comes in. You climb up a cherry bark oak to a solid branch 11.2 meters up. You hurl an acorn at, let's say, 10.5 meters a second towards your 1.4 meter tall little brother. How long until the acorn pelts the poor kid? Couple things. We draw this little picture out. I gotta draw my pretty tree. Yay, it's pretty. So the tree itself is 11.2 meters tall. And the brother is, I think I said 1.4 meters tall. And so we want to find this distance right here. And so we just take 11.2 minus 1.4, and that should give you, what, 9.8 meters? That sounds good. So that's your actual displacement, and it's going to be down, so it's a negative 9.8 meters. So there's that. Our acceleration it's in free fall. It doesn't matter whether I throw it down, up, any direction, it's always going to be negative 9.8 meters a second squared. So we already know that. So we know two values. We also know our initial velocity. And it was hurled downward, and I wrote this before I can write it in there, but it needs to be a negative 10.5 meters a second to indicate that it's going down. So, how do we set up this problem? Well, we're looking for time, right? And we also don't know our final velocity. So, different ways I could do this, but my easiest way is to do x equals v naught t plus the half of at squared. We know x is negative 9.8 meters equals negative 10.5 meters a second t minus 1/2 of 9. I'm just going to write it out. 1/2 of 9.8 meters a second squared, t squared. I'm going to move some things around and drop units for a reason that you might see here in a moment. But I should get 0 is equal to negative 4.9. That's 1/2 of 9.8 t squared minus 10.5 t plus 9.8. This is the quadratic formula. That's how you solve this. What's quadratic formula? Well, it's ax squared plus bx plus c. That's the actual way you have to set it up to get to the quadratic formula. Well, what's the quadratic formula? Let's assume you totally forgot it. Well, it's y is equal to negative b plus or minus the square root of b squared minus 4ac, and all that crap is over 2a. And so, in this case, our y is actually a t because we're looking for time. That's just the formula I learned when I was in, I don't know, middle school or whatever. So I need to find the time. So let's do that. Okay, well, t is equal to negative b. That'll be a 10.5 positive because of the negative of the negative. And then that'll be 10.5 squared minus 4. My a is going to be a negative 4.9. And my c became a positive when I rolled it to the other side, so it's going to be a positive 9.8. Otherwise, I'm going to get a square root in the radical, and that is a complex number. If you get a complex number, i.e., an error in your calculator, well, then you did it wrong. So, kind of a easy way to figure out if you've done this wrong. I'll work this one out just for the first time, and I totally forgot one thing if you're noticing, and that's the plus or minus right here. So there's that. Alright, so 10.5 squared, and that'll be a plus a 4 times 4.9 times a 9.8, because that all ends up being positive. And I root that, and so that gives me, alright, t is equal to a 10.5, and that'll be plus or minus 17.4 all over a negative 9.8. The plus or minus means you got two roots. When I take the positive root, I take the 17.4, I add it to 10.5, and divide that by negative 9.8, and I get a negative 2.84. We can only have positive time, so that root is out. So then I take my 10.5 instead, subtract the 17.4, and then divide that by the negative 9.8, and that gives me a positive 0.7 seconds. And so that one is the correct one. So if you get a negative number for time, yeah, that would be... it doesn't physically make sense, so I can't really describe it, but graphically it would, since we're finding when it crosses an axis. But in your case, you just use the positive. So the time is 0.7 seconds, and I think that's all I needed to do. There's my answer, 0.7 seconds. So, quadratic formula, good old-fashioned review for you. Okay, I'm going to do a problem where we kind of have two different velocities going on. We're going to combine the two, and you'll have one in your homework somewhat similar to this. Kind of an inspiration for this problem was this video I saw. Which I showed this last time I taught this class. So I figured, why not again? It is a failed botched robbery, but it was entertaining at least enough, and it's only like 30 seconds, but... So, yeah, he kind of drops the gun and then tries to go after it. And then he runs out, and then his pants fall down. Yeah. Luckily, nothing happened, and, well, he didn't get it anywhere. But, anywho, kind of an inspiration for that problem. Let's go back to where we're at. Okay, so a homeowner comes home, sees a robber trying to break into his house. The robber's 8 meters away, and the robber jumps on his bike and begins to pedal at 1.3 meters per second squared. So he's accelerating from rest. By this time, the homeowner is running a constant, velocity of 8 meters a second. How long will it take the homeowner to catch the robber? So I'm going to kind of draw a little pretty picture that kind of shows what's going on here. We have a homeowner, and they are flabbergasted. Why is someone breaking into my house? Dirty hippies, he says. And he lost his neck in the war. And now he's got his neck back. It's good. We know that they have a velocity of 8 meters a second, and then there's a distance of 8 meters, And there is a robber on a bike, which I really am terrible at drawing bikes. Yeah, yeah. Close enough. Lots fair. Lots fair. Okay. Um, flowing hair. There we go. Flowing hair. And they haven't need I. There we go. Okay. So, what do we do? Okay, so I'm going to call this one the distance that the homeowner will travel x1, and I'll call this one x2. I know since there's an 8-meter difference that x1 plus 8 meters, because he's going to, whatever distance he travels, he's going to need to travel an additional 8 meters to catch the robber, is going to be equal to x2. Okay, so there's my start. And then I know the formula for x1 for the homeowner is going to just be the constant velocity times time. And I'll call that v1. And then I know for my robber, it's going to be x equals v naught t plus a half of a t squared. I know that the initial velocity is 0, so that can all go away. And I should have put x2, you say, and yes, you're indeed right. All right, so they have two different relational equations. Notice that I didn't put subscripts on the time because the time is going to be the same since they both started at the same time and they finish at the same time. So what I want to do is relate these two equations. I see that x2 is x1 plus 8 meters, so I will write that in here. So x1 plus 8 meters is equal to 1/2 a t squared. Okay, that still leaves me with two variables, the variable being t and x1, but I do know that x1 is equal to v1t, so I'll say, okay, v1t plus 8 meters is equal to 1/2 of at squared. Okay, this I can work with. Let me plug in my numbers here because I haven't done that yet. This one was 8 meters a second. T plus 8 meters equals 1/2 of 1.3 meters a second squared t squared. All right, putting that into the quadratic formula because that's how you solve this. It gives me a 0 equals 1/2 of 1.3 is 0.65, and I'm just going to drop the units to make this look a little simpler. So that's 0.65 t squared minus 8t minus an 8, because I moved this and this over to the other side. Okay, so I already showed you how to do the quadratic formula already. So I'm just going to kind of skip a step and go ahead and solve this since I've got a polynomial solver on my calculator. Because that's what I bought, I guess. So, anywho, solve. That should give you two roots. Here's the fun one. So the two roots are 0.1 seconds, which obviously does not make physical sense, and 12.2 seconds. Every once in a while, you'll get a value that might not make a lot of physical sense. Obviously, there's no way at 8 meters a second he could have caught them. And so that root is clearly not going to be correct, and this one indeed is, the 12.2 seconds. Another way of knowing that is, well, if he's traveling 8 meters a second, he's already have to go 8 meters. There's no way he's going to catch him. So, anyways, 12.2 seconds is how long it's going to take to catch the robber. And that was the question. I don't need to find the distance. I just need to find how long. If I did need to find the distance, by the way, I could plug it into either of these two formulas to get my distance. So, okay. All right, let's try another one. Let's go back to gravity. Sort of. A rock is dislodged from Vesta. This is a picture of Vesta. It's one of the largest objects in our asteroid belt. I believe it's like a single digit of a percentage of the mass of the asteroid belt, so it's pretty freaking big. It's dislodged from Vesta and flung upwards around 20 meters a second, so around 45 miles an hour, a reasonable value.
what's really crazy is the gravitational well is so small there. It'll actually travel about 800 meters from the surface of the asteroid. Remember, there are 3.28 feet in a meter, so basically put, if you could throw a baseball around 45 miles an hour and you're on Vesta, you could throw a ball that's going to travel about 2,500 feet up, which is kind of amazing. Granted, you have to be in a spacesuit, but it's still kind of cool. We want to know the acceleration due to gravity on Vesta. So, a couple things I know here. I don't know my acceleration this time because Vesta has a different gravitational pull than the Earth does. I do know my initial velocity is going to be a positive 20 since it was going upwards. And I also know that my distance, x, is going to be a positive 800 meters since it was thrown up. Now, when you throw an object up, it's going to go up, 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 and eventually it's going to stop, assuming it's not going to hit orbit or escape velocity. What means, and since it went 800 meters up above the surface of the asteroid, then I know that the instantaneous velocity here must be 0. So my final velocity, or instantaneous, is going to be 0. That is helpful. One of the reasons I'm doing this problem is because we haven't used this equation yet, but we don't have time. But there is a time-independent equation. V is equal to V naught squared plus 2a delta x. We know our final, we know our initial, and we know our x. We need to solve for a. I'm just going to go ahead and write this out. V squared minus V naught squared over 2 delta x is equal to a. And now I can plug in numbers. Okay. 0 minus my initial velocity, which was 20 meters a second, all over 2 times 800. And that's equal to A. Okay. So, 20 squared is what, 400? I should do this in a calculator instead of doing it in my head, but 20 squared is 400. Divide that by 2, divide that by 800, and that gives me a negative, and it should be negative, 0.25 meters a second squared. I didn't actually ask for the magnitude of the acceleration due to gravity, but normally we wouldn't say negative. It's negative from the problem because it's always pointing towards the center of the asteroid. But when you look it up, like I think I went to Wikipedia, which is actually pretty good for NASA or for any type of astronomical data. There's not a lot of controversy in Wikipedia with astronomical data, so there's not a lot of changing of it. And so it's usually actually pretty accurate. But anyways, when you look it up, you'll see that it's like 0.25 meters a second squared. Because they don't express it as negative. It's only negative when you're looking at it as pointing towards the center of the asteroid. So, but yeah, this is actually a way that you can actually figure out the acceleration due to gravity on any object, assuming that you're there. How do we do it now? Well, if we know the mass, and this will be later on chapters, you can actually pretty easily figure out the acceleration due to gravity if you know the mass of the moon. How do you get the mass of the moon, you might ask? Well, if you know the period, you can actually work backwards to get the mass, not moon, I'm sorry, the asteroid. You can actually work backwards to get the mass of an asteroid, which is kind of neat. So, anywho, I think you have one problem where you have to do something similar in the homework where you have to find the acceleration. It may not be exactly like this, but the process should be similar. So, all right, now a fun one. All right, so we have a tiny tourist. What I mean by that is that we're not going to count its mass or its height or anything like that. With a monstrous sneeze, is propelled directly upward at 20 meters a second off of a 100-meter tall cliff. So basically put, let's pretend, oopsie, this rock is a tourist. This is Grampians National Park in Australia, by the way. So he goes, sneeze, oh no. And then he hits the top and he goes, oh no, why me? And probably dies. So, what do we know? Well, we know that the velocity at the top of the trajectory, the same thing we did from last time, is going to be 0. Don't necessarily need that, but we'll come back to that. I know that my initial velocity was a positive 20 meters a second. since he went all the way, well, he's going up. We're back on Earth, so it'll be a negative 9.8 for acceleration, pointing back towards the center of the Earth. And then I know that it's a 100-meter tall cliff. Oh, need to find my icon. There we go. Okay. All right, so 100-meter tall cliff. There's a multiple different ways I'm going to do this, or that you could do this. You could figure out the time it takes to get to the top of the trajectory, find that height, then find out how long it takes to drop all the way down. But I do know that it doesn't matter what happens up and down right here. I know that the overall displacement is going to be a negative 100 meters. And because of that, that's going to make this way easier than calculating the time it takes. Oops, let me try to find this here. Calculating the time it takes to get to the top and then the time it takes to fall all the way down. So how would I do that? Well, we have our x equation, v naught t plus a half of at squared. We know that our x is a negative 100 because it's going down. Our velocity is going up, so that's going to be a positive 20 meters a second t. And then minus, again, for the negative gravity, 1/2 of 9.8 t squared. Yeah, I lost my units there. Okay, well, quadratic again. Wow. Didn't think you'd ever use quadratic again, did you? So that's going to be negative 4.9 t squared plus a 20t. Then plus 100 once I pull that back to the other side. From here, I assume that you can use the quadratic formula. So I'm going to use my equation solver. I suppose you could if you want to program it to your calculator, or if you have a TE Casio, it does it for you. So let me see here, negative 4.9, positive 20, positive 100, solving. I get a negative root and a positive root, so I want to go with the positive root, and I'm just going to round it up and say 7 seconds. It's like 6.99. So it's going to take the tourist 7 seconds to travel this entire trajectory. So it's a really easy way of solving this without actually figuring out the height. What if you wanted to figure out the height, one of you might ask? Well, in that case, I would have to do something similar to what I did last time. I know that the final velocity is 0, and the initial velocity is that. I would have to use my v equals v naught plus at equation to get the time it takes to get to the top, and then figure out the velocity. Actually, there's another way, but that's just the one that came off the top of my head. So, anywho, that's the problem. All right, graphing. You can use a graph to find all sorts of things. Depending on if it's a displacement versus time or velocity versus time, you can find velocity, acceleration, and distance. Particularly if you find the area under the curve of a velocity graph. It doesn't necessarily have to be a curve, but let's say this is a velocity versus time. And let's say you have some sort of function. If you find the area underneath that function, you will actually get the distance. And I'll do an example on that. So that's pretty unique. And if you take the slope of the velocity graph, you will get the acceleration. So if I find the slope between these 2 points, see if I can write an M, that will be acceleration. In addition, you can find the velocity at various points in time, but there's quite a lot of things you can do, at least from the graph. So, all right, so let's do an example here. I just kind of found this a long time ago, I guess, at Indiana University. I don't really know. It just was a graph, and it worked, and I've never really changed it since. But what is the velocity at time 1.5 seconds? So if I look at this graph, it is a velocity versus time graph. And I wanted to find it at 1.5 seconds. So this is 1, this is 1.2, this is 1.4, this is around 1.5. So then I come down, and you kind of have to do this in your homework. It's literally an estimation. But it's about at its lowest point. So I think it's around 20. So I'm going to say around 20. And you got to be careful with the units. That's going to be, a couple things about the units. I didn't leave myself room here. It's 20 centimeters a second for the speed, but since the velocity is below the x-axis, that's going to be a negative 20 centimeters a second. Okay, well, what about the acceleration from 0 to 0.75? So basically the acceleration from here, so that'll be roughly here, we'll call that 21, to 0.5. Okay, so that's 0.2, that's 0.4, this is 0.5. So roughly here, that's around 8. And so I take, okay, well, that's where you take the slope. So I say 8 centimeters a second minus 21 centimeters a second. And then I divide that by the time of 0.5 seconds. Because after all, what is acceleration? Nothing more than change in velocity over change in time, as we learned earlier in this chapter. Okay, well, I take 8, and then I subtract 21. I could probably do this in my head, but I'm not going to, because that's where I tend to make mistakes. And I get looks like negative 26 centimeters a second. And I said centimeters a second, I meant centimeters per second, because there's another thing I want to point out. When you take centimeters a second and then divide it by the seconds, then you get the proper unit of second per second, or centimeters per second squared. So, and it's negative, and that makes sense because you are slowing down between those 2 points. All right, well, what's the acceleration between 2.2 and 2.6? So 2.2 is here. That's 4, and that's 6. Roughly here. And then coming across the best that I can. It's around 14. And this looks around 0. So that'll be 14 centimeters a second minus 0 over, and that was 0 to 0.75, so that'll be 0.75 seconds. And that's going to give me positive 18.7. And then, okay, I also mentioned you could do distance. Well, what's the distance covered between 2 and 2.2 seconds? Okay, here we go. Here is 2, and here is 2.2. So, what you have to do is find the... That's looking kind of nasty right there. You have to find the area, and you got to approximate it to what shape it is. And that is a triangle. And the area of a triangle is equal to 1/2 of base times height. Your base in this case is 0.2 seconds. And your height in this case, and I'm going to estimate, is around 8 centimeters a second. So I take, okay, 1/2 of my 0.2 seconds times 8 centimeters a second. Notice that your seconds cancels out because we wanted the unit of distance anyways. And so that actually kind of works out. And then you just take 1/2 times 0.2 times 8, and you should get 0.8. 0.8 centimeters. It's asking for distance and not displacement, so that's just going to end up being a positive value of 0.8 centimeters. It's actually at that point moving forward, but it's still in the negative direction. Kind of more on that later, but for this case, it's just asking for distance. So I shall do another.
Okay, so another velocity versus time graph. This is more qualitative questions. What intervals is the acceleration 0?
Okay, so this is a velocity versus time graph. Notice that it's kind of written weird. Sometimes you'll see it written as meters a second to the negative first, because I know I can bring that to the bottom and get meters a second. So you'll see that occasionally, by the way. Well, here we're speeding up. Here we're slowing down, but here we have a constant speed. This is like cruise control. And so that means if I'm not changing speed with time, then I am not accelerating. And so rolling back down here, that's roughly 2, and that's roughly 5. And so I would say 2 to 5 seconds. And then what interval is the acceleration positive? Well, I kind of already did this already, so whoopsie. But 0 to 2 seconds, it's going to be positive. And then we know from 5 to 8 seconds, it's going to be negative. And that's because if we're going back towards the origin, then we're clearly decelerating. All right. All right, so which of the following graphs of position versus time corresponds to the motion of an object in a straight line with a negative acceleration? So these are all distance versus time graphs, or position versus time, whatever you want to say. Okay, so right off the bat, there's a couple ways I could analyze this. It's asking for acceleration, right? So with a displacement versus time graph, let's start with B. B has a straight line, and we're assuming that this is distance and this is time. That means if it's a straight line and a distance versus time graph, then you have a constant speed or a constant velocity. If you have a constant velocity, then you can't have acceleration. So that right off the bat means I can get rid of B. That's a straight line. I can get rid of D. I can get rid of, oopsie, where'd you go? There you go. E. Okay, so that leaves me with two, A and C. We wanted a straight line with a negative acceleration. This is a little misleading in this case. This is kind of below the axis, but if we're going in this direction and our slope is getting more and more positive over time, this would actually be a positive acceleration because soon we're going to break through this axis and keep going forward. But in this case, our acceleration is actually getting more and more negative over time. So our answer, by process of elimination, is going to be A. So. Okay, do one from the book. I've always done one from the book. I'm not sure why. But at least on this chapter I do. So, anyways, bus travels, according to the graph below, what is the average velocity, magnitude, and direction of the bus during segments A, B, and C? And we express this in kilometers an hour. So, segment A, find my cursor. There it is. It's going from here to here. B is here to here. C is here to here. We want to figure out the average velocity, which is your change in your displacement or over time. Okay, so let's figure out segment A. So I'll call it VA. All right, so it looks like we go to 10 kilometers minus 40 kilometers, and we're going to do that over a second and a half, 1.5 seconds. Okay. And so that gives me a negative 30 to be exact, divided that by 1.5, and that's going to give me a negative 20 seconds. I see what you're saying. Yep, yeah, I caught that. Hours, sorry. Negative 20 kilometers an hour. So it's actually coming back towards the origin on the A segment. The direction will be negative. It doesn't have to be up, down, or 80 degrees north of west. In this case, it's just literally back and forth. We'll assume it's on one road and one route. All right, VB. All right, so then that gives me a 20 kilometers minus a 10
kilometers over its change in time, which is going to be 1 second, because 2.5 minus 1.5 is 1. And so that one's easy enough that I'm not going to do my calculator. That's going to give me, dang it, I did it again, hours. Sorry. 10 kilometers an hour. I'm very used to doing seconds, as you can see. And then VC is going to be 40 kilometers minus what appears to be a 20 kilometers. And that one occurs only over a period of half of an hour. Almost did it again. And so that's going to give me a 40 kilometers an hour. So it's obviously going to go fastest along this leg. So, all right, that is the last problem. I have posted homework. I need to check because I feel like there's one problem that's kind of tricky. It's a graphing one, and you have to look really closely. I don't know if I pulled the problem or not, but if I didn't pull the problem, I'll put a hint on Blackboard on what you need to do on that problem, because if you don't look at it very closely enough, you can get a wrong answer. But other than that, that's it for Chapter 2. I will hope to post the Chapter 3 lecture soon enough. It takes me a lot longer to get through these than I thought I would. When I make mistakes, I have to start over, and then I have to splice them all together through my mistakes. I guess I could just correct it in real time, but that would just be kind of annoying. So, anywho, I will try to get that posted as soon as I can for Chapter 3, but here at least is Chapter 2.